in the last video, we talked about how we can take a sum, break it up into algebra tiles, and represent that sum as a product. In this video, we're going to see how we can actually just do that without the algebra tiles. Okay, so let's pretend we had the opposite problem. Let's pretend we started with the product and got to the sum. So we're going to take a look at these two because this actually can be done. If you remember before, we also saw that you can't always turn any sum into a product. Didn't work with this one. So let's do that. So we're going to start off with the product. So we're going to use purple for product. So we're going to do 2x plus 1 times x plus 5. Now, because we already know what this is supposed to be, I'm just going to start off over here. And I'm going to say that that equals 2x squared plus 11x plus 5. Alrighty, but how would you actually do this? I'm going to use a generic rectangle, by the way. Plenty of other people are able to factor using this method called splitting the middle term. I just like that the generic rectangles provide a visual, and that really helps me, and I think it helps a good number of people. Okay, so if I was to actually multiply this, and I'm going to draw the rectangle in the middle here, because it kind of acts as our connection or our bridge between the product and the sum, excuse me. Okay, so to do this, I would lay out, again, because this is a product, one of these side lengths is the height and one of them is the base. So I'll just put the 2x plus 1 over the top as the width, and the height will be x plus 5. And now to get the sum, we need to find the areas of the individual kind of quadrants of this rectangle. So we have 2x times x, 2x squared, 1 times x, which is just x. Oh, excuse me. 2x times 5, which is 10x, and then 5 times 1, which is 5. And then if we were to collect our like terms, that's how we would get there. Okay? Let's do it again with this second example over here. This one right here. So I'm just going to copy this. Sorry, that's not what I wanted to do. Copy that right there. Copy this. Put it over here. And we're going to do the same thing. So hit equals there. So let's see, I have, again, draw my rectangle. X plus 2, x plus negative 1. So I like to write it that way so that it makes a little bit more sense. It's awkward to say, x minus 1 and then you have an extra kind of row there. But you can just write it as x plus negative 1. X times x, oops, wrong color there. Sorry about that. X times x, that's going to be x squared. 2 times x, 2x. Excuse me. X times negative 1 will be negative 1x, or just negative x. And then negative 2 there. And that's how we get to there. Okay. There are a couple observations I want to make based on what we see here. Okay? There's two. So let's write in here observations. My first one is that we can see the x squared term and the constant term actually in the generic rectangle. What do I mean by that? Well, we can see here the 2x squared and the plus 5, they're already there. We actually kind of see them right there. And they're actually in opposite corners. That's also the case over here. We see the x squared and the negative 2. And we have that right there. X squared and negative 2. So my first observation here is that the x squared and the constant term, again, the constant term just means the term that does not have an x attached to it, term appear in the generic rectangle. My second observation is not as obvious. Okay, but just bear with me. Notice the middle term here, and so this piece right here, you don't see it directly in the rectangle. You don't quite see it, right? Because I don't see 11x, I see 10x plus and an x. I don't see positive 1x over here, I just see 2x and negative 1. But I do know that I get that 11x by collecting the like terms. X plus 10x gets me to 11x, and likewise 2x minus x gets me to positive x. And so the other two boxes, here. So not only do these appear in the generic rectangle, they also appear, and they appear, let's see, in opposite corners, Our second observation here in green is that the x term is broken up in the other two corners. I'll say that is broken up. Oops, that's a little awkward space there. It's broken up into the other two corners. But that still begs the question of how do we know how it gets broken up? This is where our third observation comes in. I kind of forgot about the second one, so that's why I said there were only two before. But there's three. Check this out. If I were to multiply this diagonal, what would I get? So I'm just going to do 2x squared times 5. Well, 2x squared would be times 5 would just be, well, 10x squared. When I multiply the other diagonal, this is going to be also 10x squared. Okay, that's a little weird, funky. I mean, cool, but does that always work? Well, let's try it on this one. Negative 2x squared. That's what that one would be. Negative 2x squared. Negative x times positive 2x. Well, I think that's actually also going to be negative 2x squared. This actually indeed is going to work. If you don't believe me, try this on any random problem. So just do a plus b. And again, I don't know what a and b are. They're just magical numbers. And multiply that by c plus d. And just see what you get. Okay? But over here, and I'm just going to leave that to you to try that on your own if you're curious. Which you should be, because you should never just believe your math teacher. Just, you know. You should make them explain stuff. Make them show you why. Just in the interest of time, I'm going to skip that step in this video. But our second observation is that the diagonals, the product of the diagonals products of the diagonals are the same. So how does this help factor? Well, here's what we know, is that when you're multiplying, you have the side lengths. Again, using the generic rectangle, you have the side lengths and you provide the interiors, I'll say. When you're factoring, it works, again, like we said, the opposite. So when factoring, you have the inside, have the interiors, and want to provide the side lengths. And want to provide the side lengths. Okay, so let's actually end this with an example. All right. And in the next video, we will kind of lay it all out, write a procedure, writing, step by step, and then also do a couple more examples. The thing that I'm going to factor is, let's say, x squared minus x minus 6. Okay? Factor this thing. Okay, so again, that just means that's going to equal something times something. Okay? So we are given the sum, so I'm actually going to turn this into red. And over here, we're going to have this in purple. Okay? Excuse me. So I'm going to set up my generic rectangle. And what do I already know? Well, just like we've been noticing over here, our first observation is that I already know my x squared and my constant term are going to appear in opposite corners. I usually go top left and bottom right, but it actually doesn't matter. But I'm going to do that. So x squared here and negative 6 in here. I don't know what goes into the other two corners yet. Okay? I don't know yet what goes in here. Okay? But whatever these are, actually I'm going to change, I'm going to use a little bit of symbols here. I'm going to say smiley face and frowny face. I don't know what those are yet. But what do I know? I do know that those are going to be my x terms because I have the x squared already and I have the constant minus 6 already, but I don't have the minus x yet. So I do know that smiley face plus frowny face has to equal negative x. Okay, and so that's this second observation here. Our third one is that we know the products of the diagonals must be the same. Okay, so in this case, the diagonal, well, the first diagonal, this one, is negative 6x squared. So that means that smiley face times frowny face has to equal negative 6x squared. And at this point, there's a little bit of guessing and checking going on. So I know that if I'm going to add up to negative x, it's going to end up being something x plus something x, because that's how collecting like terms works. And that works out here because I'm going to have to do x times x to get to x squared. Okay, so what adds up to negative 1, because this is negative 1x, and multiplies to negative 6? I'll give you a second to think about that. Okay, there's your second. And so I think the numbers we're looking for here are negative 3 and positive 2. Because negative 3 plus 2 is negative 1, and negative 3 times 2 is negative 6. So this actually is going to be... Ooh, actually, let's just rewrite this right here. This is going to be... And again, it doesn't matter where you put them. Negative 3x. And then 2x there. Alrighty. Last part here is we need to find the side lengths. And so what we're going to do is we're going to pull out the factors of each piece. And what do I mean by that? Well, now we're going over the purple. Remember, this side length has to apply to this box and this box. And so what number or what factor is common to both x squared and 2x? Well, besides 1, the only other option is x. So I'm going to say this side is x. And this is a nice little puzzle here, because if that's x, to get to x squared, I need to multiply x times x again. And also to get 2x, if I already have x, that's x times 2. So that's why this side length is going to be x plus 2. Last but not least, to get to 3x, if I already have x, this must be times negative 3, and you always add the side lengths like that. And also double check that this last box works. Negative 3 times positive 2 is indeed negative 6. And so our final factored form is x minus 3 and x plus 2. So that's how you factor. Again, this was kind of a long video, but hopefully these observations you can see, and hopefully this helps and states your curiosity in terms of, hey, if I could turn a sum into a product, how do I turn a product into a sum? Alrighty, thanks for watching, folks, and I'll see you in the next video.